Good morning, guys. Today we're going to be looking at part 2 of solving quadratic equations. And today we're going to be looking at, hopefully by the end of today's lesson, we're going to be able to recognize the relationship between the roots of the quadratic equation and the zeros of the function. So the roots and zeros, these two have the same meaning. So if you use the word roots, if you use the word zeros, these two mean the same thing, and they actually have a third term that they're referred to as. These are actually x-intercepts. Okay, so if you hear the word x-intercepts, if you hear the word roots, if you hear the word zeros, they are all referring to the same thing. Usually when we solve a quadratic equation, we call them roots, and when we graph them and find the x-intercepts, we usually call them zeros, but they all refer to the same thing. All right, so let's look at the first two examples, just kind of a review of the last notes, or the last lesson. In examples 1 through 2, find all the possible roots for the quadratic equations. So find all the possible x-intercepts or solutions. Okay, so let me zoom in to example 1. And then starting off, we could ask ourselves, when we're factoring, we got to ask ourselves, is everything to one side, or do we need to move items to one side? And you usually should recognize if it's equal to 0. So since it's equal to 0, then we say, okay, yeah, everything's on one side. The next thing we want to ask ourselves is, what is the GCF? What is the GCF? Let's look at the numbers. We have 3 and 24. What can I divide both of these numbers by? They're both divisible by 3. And both of these terms both have a minimum of 1n. 1n. So that's my GCF. So that's what I'm going to divide both of these by. And then I'm going to put the GCF in the front, set up my parentheses, equal it to 0, and divide. So 3n squared divided by 3n leaves me with n. And n divided by n cancels. Negative 24 divided by 3 is negative 8. And so we have this this rule. It's called the zero product rule from the last lesson. If I'm multiplying two things, let's say a times b, and my answer when I multiply a times b is 0, that means that either a is 0 or b is 0. So that means that either 3n is 0 or n minus 8 is 0. So on the left here, what's the opposite of multiplying times 3? Dividing by 3. Dividing by 3. And so these 3's will cancel, and 0 divided by 3 is 0. Then on the right side, the opposite of subtracting 8 is adding 8. So if I add on both sides, I get n equals 8. 0 plus 8. So these two answers are my roots. Right, let's go over to example 2. So first thing, ask yourself, is everything moved to one side? If not, then I have to move things, right? And I usually like to keep the squared term by itself. I mean, not by itself, sorry. I like to keep the squared term positive. So since it's already positive, it's positive 2 squared, I'm going to move these two to the left. So I'm going to do it in kind of a combination here by subtracting 8 on both sides and adding 15x on both sides, so that essentially 8 minus 8 will cancel and negative 15 plus 15 will cancel, and I would end up with 2x squared plus 15x minus 8 equals 0. Now the next part would be checking to see if it's a perfect square trinomial, difference of squares, or the table method. It's not a difference of squares because it has 3 terms. It's not a perfect square trinomial because you can't square root 2 and you can't square root 8 or negative 8. So it has to be the table method, and it's actually something that we used to do called the bottoms up. But again, we're going to review it here. So let's see if I make the table. I'm looking for 2 numbers that multiply to give me negative 16, and 2 numbers that add to give me positive 15. So we should think of 16 times negative 1 equals negative 16, and 16 plus negative 1 equals positive 15. And so I can erase this extra part. Okay, so then we have to set up our parentheses. Equals 0. The variable is x, and the numbers that worked were positive 16 and negative 1. Now, the other thing that we did was called bottoms up, and so what we would look at is, whatever the first term was, we have to remember to divide the 2 numbers that we got by that first term and simplify it if we can. So 16 divided by 2 is 8. We can't simplify 1/2, so it stays as 1/2. But if you remember what we would do, we would say, if we have a fraction, then we would move this number to the front of the variable and get 2x minus 1 equals 0. All right, and so we get the situation where we have 2 parts here. I'm going to use a different color. Let me use orange. Let me use orange. And so we have A times B. That means we have 2 situations. Either x plus 8 is 0, or let me write it in a different place. So I want to make sure I have. So and continue over here. So we have either x plus 8 equals 0 or 2x minus 1 equals 0. And so here we subtract 8, x equals negative 8. And over here we add 1, we add 1, These cancel, we get 2x equals positive 1, and then to get rid of the 2, we divide both sides by 2. X equals 1/2. So these two answers are my roots. All right, let me zoom out here. And so this next part is talking about, if we have solutions to quadratic equations, those solutions we can call them zeros of a quadratic function. And the zeros are the x-intercepts. This is kind of what I mentioned at the beginning. So the zeros are the x-intercepts of the graph. And the solutions of the quadratic equation, whatever we're going to work out here and solve, these are the roots, which is kind of like what we were looking for up here in examples 1 and 2, right? So, so there's multiple terms here, solutions, zeros, x-intercepts, roots. They're all referring to the same thing. Okay, so if we look at this, we have the graph of a quadratic function, and this is the graph, or this is the function, sorry, that's being graphed here. And so it says the zeros of this function, the zeros of a function are the x-intercepts. They're the x-intercepts. So the x-intercepts are the zeros, and if I point them out, the x-intercepts happen at positive 3 and 7. So they happen at two x values, at x equals 3 and x equals 7. Okay, so that's one part. And then over here, if we factor this, and we can factor using the table method, right? 1 times 21 is 21. So I'm looking for two numbers. There's a 1 in front here. Two numbers that multiply to give me 21. And two numbers that add to give me negative 10. So that's going to be, negative 7 times negative 3 gives me positive 21. And negative 7 plus negative 3 is negative 10. Okay, so that means I would set up my two parentheses, equal to 0, x minus 7 on one and x minus 3 on the other. So that means that either x minus 7 is 0 or x minus 3 is 0. if I solve for x on the left, I get x equals 7. If I solve for x on the right, I get x equals 3. So my roots are x equals 7 and x equals 3. All right, so what did we show here? That I can take a function and graph it, and wherever the x-intercepts are, those are my zeros, but those are also my roots. So how did I find the roots? I took this function and set it equal to 0 and factored it into these two pieces, and then set each parentheses equal to 0, solve for x, and so I get the same answers either way. So I can graph to get the x-intercepts, or I can work the algebra out and get the x-intercepts that way too. Awesome. So let's go to the next example. I think it would be, it's going to be example 3, but there's one more thing I wanted to discuss. A quadratic equation can have 1, 2, or no solutions. So let me put some arrows here. Okay, so these are all quadratic graphs, and we've dealt with these before. They're U-shaped, and on the previous page we said that solutions, let me write it up here, solutions, let me write it in blue. Solutions are x-intercepts. Solutions are x-intercepts. So if I look at these graphs here, these 3 graphs, let's look at the first one. How many x-intercepts does this graph have? 1. How many x-intercepts does the second graph have? 2. How many x-intercepts does the third graph have? So if I look at the x-axis, did the third graph even make contact with the x-axis? So this graph made no, I'm going to say no intersection. Or no intersect with x-axis. Okay, so graphically, these are basically the 3 possible situations that can happen. If I graph a quadratic function, I can either have a graph that only touches the x-axis once, touches the x-axis twice, or doesn't touch or intersect the x-axis at all. No solutions. So in the same way, I can solve the quadratic equation, and sometimes I'll get one root, one x value. So I'm going to say one root is one x value. 2 roots is getting 2 x values. And no roots is getting no x values. So there's basically, if we look at it graphically, we have our answer in front of us. If we look at it algebraically, then at the end we check, how many x values did I have? Did I get one x value, two, or none? So let's look at example 3. And so example 3 is like the example we did just a little while ago, but nothing is set up for us. Everything we have to do. So we have to graph this function. So I'm going to copy the function 2x squared minus 2. So we don't have to state what type it is, but we can use the methods that we've done for transformations to graph it. Okay, so using the methods of transformation, we would usually make a table. And for quadratic, it was -1. Oh, sorry. That's absolute value. I'm thinking absolute value. 0, 1, 0, 0, 1, 1, 2, 4. Okay. And here we have a 2 in front. It's outside. So it's a vertical expansion. And so that means I'm going to multiply all the y values times 2. So that's going to give me 0. It's going to give me 2. It's going to give me 8. And then we're going to move all the points up. Sorry, I don't know, it's getting everything opposite today. Okay, down 2. Okay, so the parent function looks like this. But we're going to transform it using the methods from the previous test. So transforming it gives us, let me use, no, that's fine, I'll use red. So it's 0, 0, 1, 2, and 2, 8. Say 8 is up there. And then we're going to move all the points down 2. 1, 2, 1, 2. So I'm going to use a different color here. I'm going to use orange. Orange is going to be my transformation graph. Right, and then I go down 2, 1, 2. 1, 2. And over here. And I'm going to do something that I haven't done in the previous graphs, but I want to erase some things just so that we can focus on the transformation. Okay, so the transformation is this orange graph, and I'm just erasing the little bits of the parent function, just so we can focus on the orange graph. Okay, so we have the graph there. scroll up, or let me zoom out actually. And so we have the zeros of the function. So here I would just copy the function again. It's 2x squared minus 2. And so the zeros are the x-intercepts. Remember that. So where does the graph intersect the x-axis? Delete this. And so the zeros, I'll put them in blue. It would be here and here. So that's at -1 and +1. So x equals -1 and x equals +1. Alright, so now let's go to the right side, the quadratic equation. If I take the function, so I'm going to copy the function over here, 2x squared minus 2. If I take that function and I set it equal to 0, and I solve like we've been doing in the past lesson, I should get the same answers. So let's check. First thing I would ask myself is, do I have a GCF? You would say, yeah, 2. Alright, so I would divide both of these by 2. I would put 2 parentheses equals 0. 2 divided by 2 is 1. So that leaves me with x squared minus 2 divided by 2 is also 1. So x squared minus 1. Then the next thing I would ask is, this part that remains, is it a difference of squares? Is it a perfect square trinomial? Is it a table method? So what's left in parentheses, it looks like a difference of squares. Okay. So the difference of squares, we would ask ourselves, can I square root the first term? Yes. Can I square root the last term? Yes. Is there a subtraction? Yes. So then that means that if it's a difference of squares, and this is my A, this is my B, then my solution is A plus B times A minus B. So it's going to be, I'm going to bring down the 2. This 2 that was over here, I'm going to bring it down over here. 2, set up my 2 parentheses, set it equal to 0. And so my A is x and my B is 1. So x plus 1 and x minus 1. Alright. And then, one of the last things we would say is, this is A, and let me use a different color here. This is B. Then if I'm multiplying 2 times something and I'm getting 0, that means that either I have either x plus 1 is 0 or x minus 1 is 0. So this tells me that either x equals -1 or x equals 1. So I'm going to say the roots of the equation on the very top. So in this blank here, I'm going to copy this equation from the very beginning and say that the roots, the solutions to this answer are x equals -1 and x equals 1. Awesome. So let's do 2 more examples. Let's go to example 4. Alright, so example 4, we have the function f of x equals negative x plus 3 squared. So we already know the type. We know that if there's a negative in front, that's a reflection over the x-axis. And plus 3 means we're going to go to the left 3. So I already know what the parent function looks like. Or we should all know what the parent function looks like. So what's going to happen is these points are going to be reflected. And so just copy the points. On the opposite side, right? Because the x-axis is going to be like my mirror, right? Okay, and then I'm going to move all the points to the left 3 units. So it's going to be 1, 2, 3, 3, and I'm going to use orange again to get my final graph, and then from there I'm going to go here, here, 1, 2, 3, 4, here, here. So again, I'm going to erase, everything else and just keep the transformation there. And so again, my transformation is going to be in orange. Okay. So at the bottom, the first blank here would be just copying the function. So the function is f of x equals negative x plus 3 squared. And so the zeros are the x-intercepts. But there's only one x-intercept at x equals negative 3. So there's only one. So remove the plural and change r to is. The zero of the function is x equals negative 3. Okay, so now on the right side, we're going to take the function, the right side of the equation, the function negative x plus 3 squared, and set it equal to 0 and see if we can solve. But, in actuality, what can we say of something that if it's already squared, if something is squared, can't we rewrite it in the following way? So can't I put x plus 3 multiplied by itself? Yeah, and so we already have, in a way, we already have our solution because this is our A, this is our B, and so if I'm multiplying this parentheses times this parentheses and it's equaling to 0, that means, x plus 3 is 0, or x plus 3 is 0, which is the same thing, right? So if I subtract 3 on both sides, I get x equals negative 3. So the roots of negative x plus 3 squared equals 0, I should say the root is x equals negative 3. So how many x-intercepts did this have? 1. How many solutions did I have? 1. Well, it was 2, but it was the same thing. So it was the same answer, same 1 x value. Okay. Now let's look at the last example. Example 5. And so the function here is x squared plus 4. Alright, so this is an easy transformation. The plus 4 is outside, so we're just going to go up 4. So if these blue points are my parent function, then I'm going to move all these points up 1, 2, 3, 4. So I'll do, again, my transformation in orange. So if I do that over here, 1, 2, 3, 4. One, two, three, 4. And we already know it's going to do something like this, right? And so I'm going to erase all the extra notations, right? And so that's my graph. And so at the bottom we're going to write f of x equals x squared plus 4. That's the function that I just graphed. And so does it have any x-intercepts? Did this graph even intersect with the x-axis? No. So this one has, so the zeros of f of x squared plus 4, I'm going to say do not exist, right? Or you could say that there are no zeros, because the graph doesn't even intersect and will not intersect the x-axis. And so on the right side, we would take the function x squared plus 4, set it equal to 0, and try and factor. Okay, does it have a GCF? One. Okay. Is it a difference of squares? I can square root x squared, I can square root 4, but is there subtraction? No. Is this a perfect square trinomial? Well, does it even have 3 terms? And it's not even a trinomial, right? So no to that one. And the last method, the table method. Again, the table method is for trinomials, but we already established that this is not a trinomial. So none of the methods can help us factor. So we would say, if you remember, we would say that this is prime. we would say it's prime because the GCF is 1 and none of the methods worked. So if it's prime, then, we could say prime would mean that it cannot be factored. So if this equation x squared plus 4 equals 0, if it can't be factored, then we can't find solutions to it, so there are no solutions. Right, so that brings us to our last example. And so again, if there are any questions, you can bring them up in class and we can go over them. But thank you for joining me, guys. I hope you have a great remainder of your day.